In this video, I'd like to continue our discussion of inverse functions. In the previous video, we saw some visualizations that helped us wrap our heads around the concept of an inverse function. But in this video, what I want to do is dive into the algebra. Okay? I want to dive into the algebra we can use to come up with inverse function formulas. All right? So let's get started. Okay, here we go. Inverse functions continued. Let's revisit the mathematical definition of an inverse function. For any one-to-one function f of x equals y, a function f inverse of x is an inverse function of f if f of inverse of y equals x. This can also be written as f inverse of f of x equals x for all x in the domain of f. It also follows that f of f inverse of x equals x for all x in the domain of f inverse. Okay? So let's take a look at the function composition. Let's see what's happening with that. And let's use two specific example functions to analyze this. We've got the blue function f of x and the red function f inverse. Let's take these functions to the top of the screen. If the functions are indeed inverses of each other, then we have this equation and this equation. Both of those equations should be satisfied. So let's try it out. Let's start with f inverse of f of x. So we're going to take f of x in blue and plug it into f inverse. Okay, so we'll take 4x and put it in the parentheses. Okay, then we say, what's f inverse of 4x? F inverse says to take what we're given and multiply it by 1/4. So we'll take 4x and multiply it by 1/4, and we can see that the 4's cancel, which gives us x. So this first equation is satisfied. This equation is satisfied. Okay, let's try the next one. Let's try this equation here. F of f inverse of x is equal to f of 1/4 x. So we're plugging this red function into the blue function. Okay, so we take 1/4 x and put it in the parentheses, and we say f of 1/4 x is equal to something. What does f say to do? It says to take what you're given and multiply it by 4. So we'll take 1/4 x and multiply it by 4. And we can see that the 4's cancel, and it leaves us with x. So this second equation is satisfied as well. Okay? That's what happens with inverse functions. You plug x into this composition, and you end up with x. Also, you plug x into this composition, you end up with what you started with. You end up with x. Okay? Let's take a look at the graph. Here I have the blue function f and the red function f inverse. As we mentioned in the previous video, these lines are reflections of each other, right? The red line is the blue line reflected across the line y equals x. Okay, so it's a reflection across this dotted line. That's what the graph of inverse functions look like. It'll always work out that way. So let's take a look at a few points. Here we can see that the point 1, 4 is on the graph of f, because if I plug a 1 into this function, I get 4 times 1, and my output is 4. So the point 1, 4 is on the graph. And that implies that the point 4, 1 is on the graph of f inverse. Okay, here it is. So if I have a point xy on the blue line, if I have a point xy on the graph of the function f, then the point y, x is going to be on the graph of the inverse. All right? Let's see a few more examples. -2, -8 is on the graph of f. So we swap this x and y value, and we say that -8, -2 is on the graph of f inverse. And here it is. Okay, these points are reflections across the line y equals x, and these points are reflections as well. That's what happens with inverse functions. Let's take a look at a point in general, right? This is just any point on the line y equals f of x, y equals 4x. So if I have any point on this blue line, if I have any point xy on the line, then that means that the point y comma x is on the graph of f inverse. Okay? Let's take a look at a function that's not one-to-one. Okay? In the definition of an inverse function, it says that the function has to be one-to-one for it to have an inverse. Okay, so let's see what happens with this function here. F of x equals x squared is not a one-to-one function. All right? If it has an inverse, then the graph is going to be a reflection across the line y equals x. So let's take this blue curve and reflect it across this dotted line, and it gives us a curve that looks like this. All right? I don't know what its formula is, but it looks like this. All right? F, the blue curve, is not one-to-one, which implies that f fails the horizontal line test. All right, this horizontal line is crossing the curve in more than one place, so it fails the horizontal line test. And that means that the function g, this supposed function g, fails the vertical line test. And if a curve fails the vertical line test, if it intersects in more than one place, that means that g is not a valid function. Okay, g is not a function, which means that f has no inverse. All right? So that's why the requirement is there in the definition of an inverse function. F has to be a one-to-one function. All right, let's talk about the domain and range. If we have, for example, f of a equals b, okay, I have some function f, some blue function f, and I'm plugging a into the function and I'm getting out b. So the function f maps a to b. So this set right here, that's what this blob represents. It represents a set, okay? This is the domain of f, and this is the range of f, okay? So if f of a equals b, then that implies that f inverse of b equals a, right? We swap the input and output to get this. So if f inverse of b is equal to a, that means that we have a function going in this direction, okay? F inverse of this number gives us this number. So look at this. This set is the domain of f inverse, and this set is the domain, this set is the range of f inverse, okay? So the domain of f is the range of f inverse, and the range of f is the domain of f inverse, okay? Let's shift gears here and talk about how to find the inverse function formula. Okay, the first step, this is the recipe we'll follow to come up with inverse function formulas. The first step in the recipe is to write down the function formula f of x equals some expression in x. Then we replace f of x with y, and we swap x and y, because remember with inverse functions, the input and the output are swapped. Okay, so we literally take x and y in the equation and we swap their positions. Then we solve for y. Okay, we isolate y. And the last step is to replace y with f inverse of x. When we isolate y, we'll get that y equals some other expression in x. And we can call that function f inverse. So let's see an example. Here we're asked to find the inverse of the function f of x equals 2 plus square root of x minus 4. Okay? So we'll take this function and replace the f of x with y. That's the first step in the recipe. And the second step is to swap x and y. Okay? So y and x are over here. Now x is over here and y is over here. And our goal now is to isolate this y. So to do that, we need to get this radical by itself on the right-hand side. So let's subtract 2 from both sides. And that gives us x minus 2 equals the square root of y minus 4. To get rid of this radical, we need to square both sides. And that gives us y minus 4 on the right-hand side. That's equal to x minus 2 whole thing squared on the left-hand side. Y is almost isolated. We just need to do this, right, to get it completely by itself. We'll add 4 to both sides. And that gives us y on the right-hand side. It's equal to this. All right, let's take this equation to the top of the screen. And let's also swap the left and right-hand sides. Okay? Y equals this. Which means that f inverse of x is equal to this expression here. It's equal to x minus 2 whole thing squared plus 4. This is the function formula for the inverse. Okay? Let's take this equation to the left side of the screen, and let's also do some color coding. Okay, let's take f of x and make it blue, and we'll take f inverse and make it red. All right, let's graph these and see what it looks like. Okay? This is what the graph looks like. We can see that the domain of f is 4 to infinity. Now, why is that the case? It's because we can't have anything negative under this square root. So the smallest number we can plug in is 4. 4 minus 4 is 0. All right? We can plug in a 5. 5 minus 4 is 1. Plug in a 6. 6 minus 4 is 2. So those are the numbers that we can plug in for x to have the business underneath the square root stay positive. So the domain is this set, right? It's all the numbers from 4 to infinity. 4, 5, 6, 7, on and on to infinity. Okay? And the range is 2 to infinity. We can see that from this curve, right? It starts here at the point 4, 2, and it extends upward. So the y values are going from 2 to infinity. Recall what we said on the screen that had those blobs. It had those sets, right? The range of f is equal to the domain of f inverse, all right? Also, the domain of f is equal to the range of f inverse. So these are the same, and these are the same. Okay, so the blue curve, it looks like this swoosh that we've seen before, right? And this inverse curve, right, this is part of a parabola. It's a parabola with a restricted domain. The domain is restricted to be 2 to infinity, right? The x values go from 2 to positive infinity. So, because the domain is restricted, this parabola, it becomes this swoosh here, and we can see that it passes the horizontal line test. It also passes the vertical line test. So, these are my two functions. They're reflections across the line y equals x. All right, let's take a look at one more function. Here we're asked to find the inverse of the function f of x equals 2 over x minus 3 plus 4. So let's take this function and replace f of x with y, okay? Then we swap x and y, okay? And our goal is to isolate y at this point. So we're going to get this fraction by itself. So we'll subtract 4 from both sides. And that gives us x minus 4 equals this fraction, 2 over y minus 3. Next, what I want to do is multiply both sides by y minus 3. Okay, and we can see that this y minus 3 and this y minus 3 are going to cancel. And that leaves us with y minus 3 times x minus 4 equals 2. Okay, we almost have y by itself. The next step is to divide both sides by x minus 4. And this x minus 4 cancels with this x minus 4. That leaves us with y minus 3 equals 2 over x minus 4. Okay, then we add 3 to both sides. And that gives us y equals this fraction plus 3. Let's hone in on this equation right here and erase everything else. And let's take this to the top of the screen. And let's replace the y with f inverse of x. This is my inverse function. Okay? F inverse is equal to 2 over x minus 4 plus 3. Okay, great. Let's take this function, this inverse function, to the left side of the screen, and let's color code this again. All right? I want f to be blue and f inverse to be red. What do they look like on the graph? They look like this. All right? The domain of f is all real numbers except for 3, right? We're not allowed to plug 3 in here because that would give us division by 0. And I know that the range of f is all real numbers except 4 because I know that there's a horizontal asymptote at y equals 4 because this function is essentially the function 1 over x but shifted up 4 units. All right? The function 1 over x has a horizontal asymptote at 0, at y equals 0, and when we add 4, that horizontal asymptote comes up here to y equals 4. All right, we'll talk more about asymptotes in a future video. The domain of f inverse is the range of f. So these two sets are the same, and the range of f inverse is the same as the domain of f. So these two sets are the same. All right, and once again, we can see that these curves are perfect reflections across the line y equals x. Okay? That does it for this video. Thank you for watching, and like and subscribe.